Hello everyone! In sharing a story today, we delve into the intriguing world of fluid flow in the context of oil and gas, exploring complexities of multiphase behaviors and the factors that influence movement of the substances within the pipelines. Fluid flow, particularly in pipelines, is influenced by a multitude of variables. To design pipelines effectively, researchers must comprehend the intricate interactions and effects of these variables. This demands a wealth of experimental data, often obtained through complex procedures. In the rim of oil reservoirs, the fluid can be classified into three distinct phases: water, oil, and gas. When drilling and completing a well within an oil reservoir, the oil begins to move up through the tubing. This journey brings about changes in the physical conditions within the reservoir, including evolution of gas from the oil and the possible introduction of water and gas into the tubing. The result is multiphase flow, a phenomenon where a well initially completed as a single-phase oil experiences the coexistence of multiple phase due to evolving conditions. Now imagine a simple phase diagram where temperature and pressure serves as the axes. At lower temperatures and high pressures, the fluid predominantly exists in the liquid phase. As the temperature increases, the transition to gaseous phase occurs, maintaining its state even as pressure decreases. At intermediate pressures and temperatures, both gas and liquid phases can coexist in varying proportions. By observing specific points on the diagram and altering conditions such as increasing temperatures while maintaining pressure, we witness transition from single-phase liquid to eventually single-phase gas. This transition is reversed when reducing pressure while keeping temperature constant. When fluids are extracted from a reservoir, pressure reduction occurs, often leading to the formation of bubbles as the system enters the two-phase region. As oil ascends to the surface, pressure and temperature conditions change significantly. Assuming the reservoir initially contains predominantly liquid, the transition to a two-phase mixture occurs as pressure drops. A similar scenario applies to the reservoir with predominantly single-phase gas, where surface conditions can cause phase transitions. To manage this, separators are installed at the wellhead, facilitating segregation of different phases into separate pipelines. However, even with separators, single-phase flow isn't guaranteed through the pipeline, as further changes in the temperature and pressure can lead to the reemergence of multiphase behavior. Condensates, low-density liquid hydrocarbons, often accompany natural gas. Their presence depends on the temperature and pressure conditions, leading to condensation from vapor. Managing reservoirs with condensates can be intricate due to the pressure sensitivity. If reservoir pressure drops below the dew point during production, condensates can change from gas to liquid. To prevent this, reservoir pressure is maintained through the fluid injection, prioritizing gas production over liquid. Gas produced alongside condensates is termed as wet gas, with the condensates typically exhibiting an API gravity between 50 to 120 degrees. The flow of oil and gas within pipeline is a complex dance of phases influenced by various factors. Understanding phase diagrams, transitions, and the impact of pressure and temperature changes is vital in designing and managing oil and gas systems effectively. Another crucial determinant of fluid flow is flow patterns. Gas-liquid two-phase flow behavior plays a pivotal role in various industrial processes such as chemical, petroleum, and HVAC systems. These flows involve a complex interplay between gases and liquids within pipes, presenting unique challenges and opportunities for analysis and design. To determine the amount of gas and liquid being transported through a pipe, we need to comprehend the state of the mixture at each point along the way. When exploring gas-liquid flow, we encounter various flow patterns that define the behavior of these mixtures under different conditions. These patterns are influenced by the orientation and direction of flow, including concurrent, countercurrent, upward, and downward flows. For instance, envision a horizontal pipe carrying both gas and water. At lower gas and liquid speeds, A stratified configuration occurs with the liquid flowing at the pipe's bottom and the gas above. As gas velocity increases, waves form at the interface affecting pressure drops. Other patterns emerge, such as the appearance of long bubbles at low gas rates or the development of highly aerated liquid slugs at high rates of both gas and liquid. In practice, avoiding such slug flow patterns is crucial due to the potential for damaging vibrations. At extreme high gas speeds, an annular pattern arises where liquid forms a film of the pipe's inner surface with the droplets entrained in the gas core. These flow patterns and their associated flow maps hold significant importance in industrial applications. They aid in predicting flow rates, pressure drops, and behaviors in various scenarios. One prominent application of these maps lies in nuclear reactor design, especially in scenarios like loss of coolant accidents. Engineers use these maps to analyze the behavior of liquid and vapor phases within pipes during heat transfer processes. In nuclear reactors, the transition from liquid to vapor, characterized by the onset of boiling, leads to complex flow patterns. For example, as subcooled water enters a vertical tube subject to constant heat flux, bubbles start forming, coalescing into liquid slugs, and eventually transitioning to annual flows. These flow patterns have critical implications for reactor safety and efficiency. By studying these patterns using flow maps, engineers can better understand heat transfer processes, predict critical points like dryouts, and ultimately ensure the safety and optimal performance of industrial systems. In conclusion, gas-liquid two-phase flows offer a captivating fluid dynamic that underpins numerous industrial processes. Through careful consideration of flow patterns and their associated flow maps, engineers can gain insights into behavior, predict critical points, and optimize system designs. These flow patterns not only guide in understanding complex phenomena, but also plays a vital role in ensuring safety and efficiency of a wide range of industrial applications.